Problem 3. The original signal was modified to a periodic signal from 0 to 2. In part A, to obtain the Fourier transform was necessary made a derivative transform g omega that is divided in j omega, corresponding to the integral of the derivative, and of this way obtain the Fourier transform. The derivative transform is composed by g1 omega plus g2 omega, each one as a part of ft. The function constructed for differentiating this segment to obtain impulse functions. In g1t, were obtained two impulses. In 0, an impulse of 1, and in 1, an impulse of 2 negative. By this, in g2t, the derivative of t minus 2, this function, is 1, representing by a unit step. Then, with the second derivative, generate two impulses of 1, positive and negative. In the same way by the displacement. And of this way, with the derivative transform, the first part of this derivative transform, g1 omega, is equal to 1 minus 2 Euler minus g omega by the properties, and g2 omega dot is equal to Euler minus g omega minus Euler minus g omega 2. But taking in account that g2 omega is equal to the derivative over g omega, because it's necessary to integrate the derivative transform to obtain the real value. Of this way, with the derivative transform original, substituting the values, the derivative transform g omega is equal to 1 minus 2 Euler minus g omega plus Euler minus g omega minus Euler minus g omega 2 over g omega. Since, as mentioned before, it's necessary to integrate the derivative transform to obtain the Fourier transform that is indicated by this expression. And with Wolfram, the reduction of the terms is equal to this. In part B, the defining integral is indicated by the following, where in the expression the function of the original signal are replaced with their corresponding periods. With this, we observe that the result of the Fourier transform obtained by the defining integral is the same with the obtained by the transform properties using Wolfram. Then the MATLAB code in part C is described by the following. Consists in define the original signal in time domain with unit steps, then the representation, and then in frequency domain use the function do Fourier transform, and the parameters are ft, the original signal, and t, because it's in time domain. With this, the transform is represented with this plot. The MATLAB code in part D is the following, including the expression obtained in part A with the Fourier transform properties, the respective representation, and the expression obtained with the defined integral, and we can see in the plot the results are the same.